every action has equal and opposite reaction. So that means whenever you are applying a force, or if you are trying to push a wall in a forward direction, the displacement of wall is zero, right? The wall will not move, but the force which we are applying on the wall, the same force will be acting in our hands. That means there will be a reaction force. So similarly, when we are standing on a ground, our weight is acting in downward position, our reaction force is exerted in upward direction by the earth. So similar type of applications of Newton's third law of motion we are going to learn today. So watch the video till the end. Okay, so let's start our class today. So application of Newton's third law of motion. So you see, I have noted down in the board some condition, case 1, case 2, case 3 and case 4. So one by one we will go through. First of all, what is this application you see? So let us consider there is one lift, right? So this is one lift, and inside the lift you are standing, right? So this arrowhead shows that you are standing on the inside the lift. Now there can be 4 conditions. Like for example, if the lift is not moving, you are standing inside the lift, your weight is acting down, right? So as you are standing on the lift, weight is acting down, a reaction force will be produced up, right? This weight is given by mg, right? Weight equals to mass into acceleration due to gravity. So when the lift is stationary, so net force is 0. So this is the first condition which I have taken. Okay. Here I have said what is the apparent weight of the body moving in a lift. That means apparent weight of the body. So 2 types of forces will be acting on that object. First, your weight will act in downward direction, and reaction force will act in upward direction. These are the 2 forces, right? Next, first condition is that when the lift is at rest. When the lift is at rest, the total force or the net resultant force on the lift is equals to 0. Why? Because the formula says that R minus mg equals to ma. That is net force equals to R minus mg. R is the reaction force and mg is the weight. As the lift is in stationary, so we'll say the acceleration is 0. So if I substitute here 0 in this equation, if I substitute, that means R minus mg, m into 0, 0. So R equals to mg. Oh, okay. So directly we can say that when the lift is at rest, reaction force equals to weight. So that is the reaction force equals to weight, right? R equals to mg. Now next condition, the lift moves up with uniform acceleration. Now the lift is moving up with an uniform acceleration, not with uniform velocity. Okay, this one you have to note. If it is uniform velocity, then the condition will get changed. So if a lift is moving up with uniform acceleration, so what is the formula? Net force. mm is here net force. So net force is R minus mg, because now the object is moving up. So if an object is moving up, this lift is going up, that means R must be greater than the mg, right? The reaction force must be greater than the mg, then only the object is moving up. So R minus mg equals to ma. If mg goes that side, the minus will become plus. So from here, if I take m common, then R equals to m a plus g, right? That means the reaction force. That is why if you are in a merry-go-round, if you are going in a mela or a fair, when you are sitting in a merry-go-round and it is rotating, once you go up, you feel that you have gained weight, because the reaction force, the acceleration here, this weight is increasing. Okay. But similarly, when it is falling down, we feel that our to be as weightless. Okay. So that condition also we will see. Now next condition. So first condition was when the lift was at rest. Second condition is when the lift is moving upward in uniform acceleration. Third condition is saying that when the lift moves up or down with uniform velocity. When it moves with uniform velocity, now velocity is not changing. If velocity is not changing, therefore acceleration is 0. So what is the formula? R minus mg equals to ma. The same condition, R minus mg equals to ma, a will become 0. If a will become 0, that means reaction force equals to weight. So same condition we will get here, R equals to mg. So R equals to mg for 2 conditions. When the lift is at rest, that time also we will take reaction force equals to weight. And similarly, when the lift is moving up or down with uniform velocity, then also we will be taking as reaction force equals to mg, R equals to mg, right? So fourth condition is that when the lift is moving down with uniform velocity. In this case, when the lift was moving up with uniform acceleration, we took this one for moving up or down with uniform velocity, and next we see that when the lift is moving down with uniform acceleration. So when the lift is moving down, definitely W, this factor is more than reactant force. So that is why I wrote mg minus r equals to net force, that is ma. If I take r that side, ma this side, that means mg minus ma. If I take m common, what you will get? G minus a. R equals to m, g minus a. So these are the four conditions, right? Now there can be any special case. Suppose your lift is coming down. Now on its way, the cable of the lift gets break. Okay, so if it gets broken, then what will be the reaction force? So you see, when an object is falling freely under the action of force of gravity, so we say that its acceleration becomes acceleration of due to gravity. That what I mean to say, that is a becomes equals to g. So this was a was the acceleration of the body which it was falling. So when it is falling freely, its acceleration becomes acceleration due to gravity, because it falls according to the acceleration due to gravity. So if this lift is falling down and the cable has broken, so it will act like a freely falling body, and the acceleration of freely falling body is 9.8. that is acceleration of freely falling body, we can say that is small g. Now if I substitute here, now one more condition, if I place here when the lift falls freely, its acceleration a becomes g. Okay, its acceleration a becomes g. So what will be the reaction force then? R equals to m g minus a when the lift is falling down. Now here if I substitute, that is here a equals to g. So m g in place of a, what I will substitute? G minus g, 0, 0 into m, 0. That means reaction force is 0. So that is why we feel weightless, right? So when in a merry-go-round also, when we rotate, when we go up, we feel that we have gained weight. But as soon as when we come down, we feel that the lower portion of our body is vanished. That means we feel weightless here. Why it is so? Because here the reaction force is 0, right? So when we go up, when the lift is going up with an uniform acceleration, the reaction force increases. When the lift is going down, the reaction force decreases. So this was the first application. The next application we will see the motion of the connected bodies. When two masses, one is m1 and m2, when they are connected by a string having a tension of T and which is passed by an inextensible pulley. Okay, so here it is being seen that the mass of m1, this body, is more than this body. Now if I consider the acceleration of only mass m1, as this mass is greater, so when it is falling downwards, this is moving in upward direction. Okay, so as this is falling downward, that means the weight of this must be greater than the tension, okay, which is equals to the net force acting on this body. So what is the net force acting on this mass m1? That is m1a. So when this body comes down, then what will be the equation then? m1g must be greater than T equals to m1a. Okay, so let's see what will be the tension acting on the string and what will be the acceleration of the system, right? So first you see what I have written, a vertical motion. It is a vertical motion because this object is moving down and this object is coming up. This is a vertical motion. Next we have a resultant force. That means m1g is greater than m2g. That means this weight of this body is greater than this weight. That is the resultant force. Now in order to calculate the acceleration of the system, from here m1g minus m2g, I have taken g common. Now what will be the acceleration of the system? Acceleration of the system, that is F equals to ma, or A equals to F by total mass. That F is given by this, right? And total mass, that is m1 plus m2. This is equation number 1. Now you see, if I consider only the motion of for m1, only we are not making an equation for m2, just we are considering for m1, that is considering the motion of only body 1. So this object is falling down, therefore m1g is greater than the tension, this weight of this body is more than the tension that which is acting on the string, that is why it is falling down, and this is equals to the net force acting on that body. So net force acting on this body, that is what is the mass of it, that is m1, and acceleration is a, that's m1a. Now if I take tension that side and if I change this side, right, if you see properly, m1g minus m1a equals to t, or this can be written as t equals to m1g minus m1a. So from here if I take m1 common, what I will get here, g minus a. So this is the tension acting on this string. Now m1 as it is, g as it is, in place of a acceleration I am substituting this whole part, right. Now from this equation I can take g common. If I take g common, what I will get here, 1 minus m1 minus m2 by m1 plus m2. Now we are taking LCM. If I take LCM, m1 plus m2 is the LCM. Cross multiply m1 plus m2 into 1, m plus 1, m1 plus m2, minus m1 minus minus plus. So m1 and m1 got cancelled. What we got? m2 plus m2. That means 2m2. And outside we have m1g. So 2m1 m2g by m1 plus m2. So this is the total tension acting on the string, right. So this we get in a numerical question, like what is the, like two bodies weight will be given, what is the tension acting on the string, or what will be the acceleration of the body, right. So these formulas you have to remember. Connected bodies. Now horizontal motion. You see one mass is resting on a table and one mass is being connected with a thread having a tension T, which is passed over through a pulley and which is further connected to the other mass M2, right. Now just now we have seen when the two masses were connected in pulley and there was a vertical motion, we got acceleration as m1 minus m2 g by m1 plus m2. So this was the acceleration which we got when both are passing through a pulley and one is going down and one is going up. But here in this case you see this is resting, okay. So the mass of this body which is on the table will not come into effect in acceleration. So if I consider here m2 as 0, then what I will get here, m1 g m1 plus m2. That is the resultant force which is acting on the system for producing acceleration, is acceleration equals to m1 g by m1 plus m2, right. Now you see when this object is coming down, there is a tension producing this string, and this tension is equals to force acting on this body. That means what is the force acting on this body? That is m2a. This m2a becomes equals to tension. So when these forces becomes equal, so this object remains still, it does not fall down, right. So this tension is being withstood by the force of this, that is T equals to m2a. So considering only the motion of m2, means I am not considering this motion, I am not considering whether it is going up or whether it is going down, just this is still. And because this is still, because the tension, the force which is acting on the string is being balanced by this force, resultant force on this mass m2, right. So m2a equals to tension. So what will be the tension acting on the string? Tension equals to m2 as it is. In place of acceleration I will substitute this, right. So tension equals to m1 m2 g by m1 plus m2. So these are the acceleration and tension which is produced in horizontal motion and in a vertical motion, right. So for this video only this much. In the next class we will learn what is linear conservation of momentum and numericals, okay. So till then you write the notes in your book, you have to write whatever I am teaching here in these topics, you have to note down, you can refer book, you can add there more as per your understanding, right. So you can select from here the topics which I am teaching here, you write these notes, as well as from your side you write note from the book, okay, for better understanding. So see you soon in my next video.